And just to ensure everyone's informed, we will be recording this event as well.
Okay, I didn't mute myself deliberately. That just seems to be something that the software seems to have done. Okay, let me get back to my slide pack and then we can start this thing. Okay, so just very briefly, I've been in the company 33 years. I was involved in laboratory studies for quite a long time, mainly around chemical sand consolidation, mud lubricity, shale stability, formation damage remediation, qualification of sand control systems. I did lots of things, and then I moved into the modeling arena. I was in the central support team for system modeling and optimization between 2003 and 2016. And 2016, then I joined the Rumaila team as a ESP specialist, and then subsequently became the Petroleum Engineering discipline lead. So I'm responsible for maintaining the quality of the work that we do. I provide lots of coaching and training. I help people progress their careers. I develop procedures for the field. This kind of activity. So doing this kind of thing is quite natural to me. So hopefully people will find this is interesting. What I'm going to be doing is I'm just going to be providing a very quick introduction to Prosper, the software that we use for well modeling. We're going to be building a model, talking about the various modeling choices you might need to make, running some calculations and diagnosing whether our well is a healthy well or not. And if there's extra time, then we might be able to then delve into other things. But if we run out of time and people would like more of these sessions where we can talk maybe about artificial lift or water injection or something like that, we can always arrange for another session. So Prosper is an application within the integrated production modeling suite from Petroleum Experts Limited, who are based in Edinburgh. They refer to themselves as PEDX, and most people just refer to them as PEDX. So Prosper is the well modeling application that we use, but there are other applications in the suite as well. There's famously MBAL, that's well known for material balance reservoir modeling, and general allocation program, otherwise known as GAP, that's used for surface network modeling. And GAP can integrate the well models and the reservoir models, so you can do system modeling, not just optimization on a well by well basis, and also you can do production forecasting as well. So Prosper is a very well known industry standard tool for steady state well modeling, and we can use it to very effectively assess inflow performance relationship modeling. That's fluid flowing from the reservoir into the well, and also vertical lift performance modeling, otherwise known as tubing performance, of fluid flowing in the well to surface in whatever flow conduit you happen to have. It could be tubing flow or annular flow or combination. And the purpose of well modeling, of course, is to support our technical understanding of the well and help us support business decisions. So we can calculate current and future well performance, is what we're going to try to do today. You can assess completion efficiency as well, artificial lift efficiency, and specific calculation routines you can run to do that. We can assess the appropriateness and benefit of well work. Say, for instance, you want to add perforations in the well and add a layer, or maybe you want to take a layer away because you're going to be doing some water shutoff and you want to see what is the resulting well performance. And we can also generate suites of VLP curves or tubing performance curves for use in network and reservoir simulators. And they don't necessarily have to be used in GAP. You can export them in various formats for software applications which are not even being developed by PEDX, they've been developed by other companies. So the general workflow in Prosper is, as you'd imagine, relatively straightforward, but the software itself can can throw people off a little bit. It's actually quite easy software to use once you get used to it. You basically start with selecting high-level options. I should go through a quick list of what the high-level options are, and then we're going to get into the software itself. You'd enter your PVT data and set up a PVT model. You then move on to either entering your inflow performance relationship model or enter your Wellbore description, which is basically your vertical lift performance data. You can do it in either order, doesn't really matter. You can do vertical lift performance stuff first. Once you've done that, you can enter artificial lift data if you're using it. It could be gas lift, it could be ESP lift, jet pump lifted models. There's lots of options. And included in the IPR modeling, you can include sand control modeling if you want to model that explicitly as well. You then move to matching the model to well test data if you have well test data to make your model as accurate as possible. If you're trying to model, obviously, a kind of a well that may not be drilled yet or something like that, then obviously you don't have that available to you. You just do the best you can. And once you've done that, then you can perform calculations to show how the well would react in different circumstances, which is what we'll do a bit later on. So the main screen in Prosper is a kind of a sequence of these boxes. They don't have to be gray. You can kind of customize the font and the font size and the colors. And there's lots of things you can do. Optionally, you can show a Wellbore schematic on the left, which is populated once you've put in your Wellbore description, but there's not much you can do with it. And since it tends to make the software a little bit slower to start up, I tend to turn that off. So what I normally see is just these other gray boxes that you see. So top left, you can click in here and you can enter your main options. Top in the middle, you can enter your PVT data. Top right is your IPR model. Bottom left is your VLP data. And if you've turned on artificial lift as well, then that box kind of halves in height, and then half of it then becomes occupied with artificial lift input. In the bottom in the middle is just easy access to various common calculation options, although there are more available to you from the drop downs at the top. And the bottom right there just tells you about the version of Prosper that you're using, the contact details for petroleum experts, telephone numbers and that kind of stuff. So the main options. Once I've gone through this slide, we'll leap to the software and we'll start constructing a model, and then I will then come back to my slide pack periodically to explain what some of the other modeling options mean. So there are options in Prosper for different kinds of fluids. So you can model oil, gas, or retrograde condensates, and you can also model pure water as well. That comes under the oil option. You can model either production or injection. You can have a single bore or a multilateral completion, which obviously affects the IPR and the VLP. So multilateral completions obviously are wells that have a common upper part of the well, but there's a junction downhole, and you may have one or more, well, usually two or more branches at the junction. And there are ways and means of modeling that in Prosper. It's a little convoluted. You have to kind of create icons and you connect them all together. And you can do some very interesting analyses actually with that. Even if you're just modeling a single wellbore, you get some results from that model that you can't get from any of the other models. We can model cased hole or open hole completions, which could be very simple in approach or more complex approaches, including multiple layers and fractured completions. We can model different flow conduits, tubing flow, annular flow, or both tubing and annular flow. We have those options available to us in Rumaila because we typically have wells without packers, although that is going to change over time. Elsewhere around the world, most wells have a packer to protect the annular space, and the production will be basically up the tubing. And you can assess vertical lift performance, of course, using various multi-phase flow correlations, and you choose the appropriate correlation for your fluid type and the kind of flow regimes you expect. The PVT modeling, well, you can either do that with a black oil correlation approach or an equation of state. Most of the time, black oil modeling is quite appropriate, but if you have particular retrograde condensates or volatile oil systems, then maybe a black oil PVT model is just not quite good enough. Sometimes you need to enter an equation of state instead. But we'll just be looking at a black oil model today. But we will assess which black oil PVT correlation is going to be suitable for the fluid that we've got. As far as, so going back to VLP, we can also enter surface equipment into Prosper as well, and that will include chokes and things like that. But quite honestly, I prefer to keep the well modeling to the well modeling and leave gap to handle surface pipe work. Then we move on to what kind of what does the well look like, basically. So it could be vertical, it could be deviated, you can even have horizontal flow. There are various sand control modeling options, which are basically incorporated within the IPR model. Loads of different artificial lift methods, and you also have the ability to control what kind of temperature modeling do you want to do. Either through first principles, via any enthalpy balance, or there's a so-called rough approximation method. That's the kind of terminology that PEDX uses. The method isn't rough as such. It's just the name they've given the method. It basically allows you to tune the model to well test data so you can establish a suitable overall heat transfer coefficient. If you need to account for more interesting kind of heat effects or heating or cooling effects like Joule-Thomson, for instance, then you'll need to use improved approximation. And in that methodology, you can actually assign different heat transfer coefficients to different parts of the wellbore. It kind of depends on what you want to do. Okay, so we'll start with the software itself. So you can see I've just got these boxes, and they're kind of empty at the minute because I haven't visited first the options summary. So you can either go options, or you can just simply double click in here. Just need to cough. And in here, we can choose these various things that we've been talking about. Fluid, the PVT method, whether you have, usually it's single stage separator is what we choose here. For oils at least. Essentially what you do is when you create a black oil PVT model, which you tend to export from an equation of state model, you take into account the separation pathway of the field itself, because the separation pathway that you choose to use basically ends up allowing the fluid, or you end up with a fluid at stock tank conditions, which either has less or more gas still entrained in it. And the more separation stages you have, the more gas will end up being entrained in the gas at stock tank conditions. So you take that into account when you construct your black oil PVT parameters, your inputs via your equation state model. And so you don't need to choose different kinds of numbers of stages here. Single stage is what you want to go for. And then you got some various warnings for emulsions. PVT warnings will be things like hydrates and things like that. And if you want to model those, you need to enter additional data into your PVT model. We tend to use the default water viscosity model, and obviously oils and Newtonian fluids. We just leave that as it is. Now, the model that we're going to be constructing today is an oil well with tubing flow. It's a producer naturally flowing, so an artificial lift. It's an offshore well, so we can just leave that predict thing up here as offshore. But we do want to calculate pressure and temperature. If you ever see a model that is kind of temperature or pressure only, or some of these other options in here, I've never used them. Not pressure only, for instance, it's no, you don't want to do that. Quite honestly, if rough approximation is the method you're using, then it doesn't matter whether you choose kind of on land or offshore here. It's the same result, but if you are going to go with enthalpy balance or improved approximation, then it does make a difference whether it's on land or offshore. So you just choose the appropriate one. Where it says full range here, full system, you can basically turn Prosper into kind of pipeline modeling software rather than well modeling. And so some of the options are removed from the system if you're only trying to model a pipeline. But we want full system. Brine properties, I'll just leave that on default. Is cased and perforated. We're not going to be modeling sand control explicitly as a single branch well. And that's basically it. And you can put in here company name, field name, name of the analyst, date, and all this kind of thing. And you can enter in here comments that might be useful for other users of the model. And if I click date stamp, for instance, a little date stamp appears in here as well. So for this particular model, I actually don't need to change any of the default settings, and normally only need to change a few, not too many usually. And once you've done that, then the rest of the model then starts to become active for you. You can start entering some more data. So effectively, you kind of work left to right along these drop downs. We've done options. We're going to move on to PVT. Then system is entering IPR data, VLP data. Then we'll enter some well test matching data. We'll match the model, and then we'll run some calculations and see how healthy the well is. There are design options as well, so you can use Prosper in helping you select an appropriate ESP, for instance, or a gas lift system. You can design that. And stimulation is something that popped into the software recently. This allows you to do kind of scoping studies for various stimulation routines. So without further ado, I'll just go to PVT input, but I'll have to go back to my slide pack after a while. So when you come in here, these boxes become kind of different colors, kind of depending on what you want to enter. Yellow is basically on the edge of a allowable range because you can control in here your unit set, whether it's metric or imperial. And if you enter things, you can control the range as well. So for instance, angle in degrees would be from 0 to 360. So if you were to enter 361 in here, for instance, if you try to click done, Prosper will warn you that you've entered something inappropriate. You can actually change the ranges as well, but you have to be a little bit judicious in how you want to do that. And most of the time, I don't need to touch those. So for this particular well, the solution GOR is 680.9. Oops, I typed the wrong number. That's a good start. Standard cubic feet per stock tank barrel. And if I click on that, it's not on the edge of a range, which would be yellow. It's turned green because it seems to think that this number is appropriate. This red color is bad. We can't really calculate anything with values that don't really make any sense, and have 0 oil density and 0 gas density is obviously nonsensical. So the oil gravity for this well is actually 41 point, oops, yeah, nothing happening, 41.96, good quality oil. And that already starts telling you what kind of PVT correlations you might want to use, as well as what kind of VLP correlations you may want to use. The gas gravity, 0.739. It's a little bit richer than methane. And the water salinity here is 152,000 parts per million of sodium chloride equivalent. It's just really basically for a density calculation. You can actually right and click on any of these boxes and change units on the fly. And you could enter specific gravity directly if you really wanted to, but we're just going to have part per million. And we do have some inorganic gases as well. We don't have any H2S here, but we do have a little bit of carbon dioxide, 2.96 mole percent. And nitrogen is going to be 0.41 mole percent. Now, at the minute, there are some default black oil PVT correlations in here, but we don't know yet whether Glazo and Beal are going to be suitable for this fluid. So once we've entered this high level data, and the black oil approach is predicated on knowing the solution GOR, the oil gravity, and the gas gravity, and from that the correlations are going to be able to calculate other fluid properties for us. And the correlations have been developed based on studies of fluids usually from certain regions. So if I head back very briefly to my slide pack, and look at another slide. These are a description of the black oil PVT correlations you have in here. And of course, these are all just based on papers that were published. So Glasgow, for instance, was built basically using North Sea reservoir fluids for the study. Standing was based on reservoir fluids from California. Lassiter, that was built from considering reservoir fluids from Canada, West and mid-continental USA and South America. It's quite an interesting correlation because it's been shown to be quite suitable for the heavier oils with API gravities of less than 25 degrees with low initial solution GOR. Or on the other end of the scale, it's also quite good for volatile oil systems where your initial solution GOR is more than 2,000 standard cubic feet per stock tank barrel. Not very good for the oils in between. So this is a good quality oil with not a very high GOR. So I'm already thinking this is not a Lassiter fluid. Vasquez-Beggs was actually a kind of almost kind of global average kind of correlation. Petrosky and colleagues, they built their correlation based on fluids from the Gulf of Mexico. Almahoon, not surprisingly, that was from fluids from the Middle East. And De Ghetto was considering reservoir fluids from the Mediterranean basin, Africa, and the Persian Gulf, suitable really for kind of heavy oils and extra heavy oils. So again, this is not a kind of correlation that I would want to use for this fluid. It's going to be one of the others. And for viscosity, so these correlations here are used to calculate a bubble point and solution GOR and formation volume factor, whereas viscosity is a separate choice, and you've got different correlations to choose for that purpose. Beal, Beggs, very widely applicable. Petrosky has shown to be quite effective for reservoir fluids in the Gulf of Mexico. Egboga, that's a heavy oil correlation. Bergman, Sutton. It can be widely applicable, but you generally need matching to get it to work properly. And De Ghetto and De Ghetto modified, these are again fluids for these heavier oil systems, these more viscous systems. For gas, system gas PVT, you've got basically two choices, Lee or Carr. They're both very usable. If you don't know which one it is, then just go for Lee. So how does this manifest itself in the software? If I head back here, what we need to do is we need to enter some match data, and I do happen to have some data generated as suitable for use for a black oil correlation. So we click on match data, and we just need to set up a table that represents a certain temperature, and for us is going to be reservoir temperature. So this is 215.9 Fahrenheit. And we also need to specify the bubble point pressure, which for us is 2827.7 psig. Then we need to fill in a table. And if you've got the software arranged so that the columns in the right order in the right units, you can just kind of cut and paste from Word or Excel or something like that. I'm just going to do exactly that. Helps save a little bit of time. You right click in here and just hit paste, and you get some numbers. And here we are. So one of the rows in the table has to relate to the bubble point pressure. You can get away with not specifying other data, but because the bubble point pressure is such an important part of the phase diagram, you do need to specify that more accurately. And hopefully you've got other rows in here as well that describe the fluid properties for different pressures, but at the same temperature. Theoretically, if you fill up this table, you can just create another one, give it the same, for instance, same temperature, same bubble point pressure, and then carry on filling in more rows. On rare occasions, you might need to create tables for other temperatures, but people don't generally tend to use that. And sometimes black oil modeling doesn't tend to get oil viscosity very well. And if the model is kind of really struggling, sometimes you kind of delete other rows for the oil viscosity data as well. So here we do have, for instance, various oil formation volume factor numbers, but not oil viscosity numbers. So once you've done that, you can quite happily click done, and then we move on to the next button along, the one that says matching, which really is tuning the correlation to your PVT data. And once you do that, you've got this rather busy looking window. Kind of ignore most of it. I'm just going to hit this match all button. And what we've done here is apply tuning parameters to each of the PVT correlations so you can better calculate the numbers that we've already measured. So you can then look at the parameters box in the first instance to get a feel for how well these things have been matched. Parameter 1 is a, well, for bubble point solution GOR oil formation volume factor is a multiplier. Think of Y equals mx plus c, right? So 1 is a multiplier and parameter 2 is a shift. And ideally, the multiplier should be as close to 1 as possible, and the shift should be as close to 0 as possible. If it is, then basically the correlation without much tuning is able to calculate your reservoir parameters. And here again, you can see the standard PVT correlations have been chosen for us. We keep an eye on the time, half an hour, okay. Basically, what we do is we look through this table and see, well, which of these correlations has been tuned the least. But we can't choose different ones for bubble point solution GOR formation volume factor, so we have to choose one that's kind of on average the best. If I look through here, 1.01, 0.98, and 1.03 look pretty decent, and the shifts don't look too high. But some of these other calculations look worse, especially the correlations that are more for kind of the heavy oils. They're not a very good fit. So, standing 1.08, 0.82, 0.94 is obviously not as good. 1.13, 0.78, 0.94, don't like that as much. Vasquez-Beggs is not bad, 0.97, 1.06, 0.97. Basically 1.19, that's not very good, 0.95. And you just keep going through here, and then you eventually conclude that basically Glasgow seems to be the correlation that calculates our data pretty well. And for viscosity, we have to make a separate choice. Now, unfortunately, we've only got one viscosity data point, so we're just going to have to go with whatever's been tuned the least. And for this particular model, I'm just probably going to just conclude as Petrovsky, because 1.12 seems to be sort of closer to 1 than some of these others. So I make my choice here. It's basically Glasgow, and I choose Petrovsky et al. If I hit done here, nothing basically changes here, but this tab was introduced in Prosper a few versions ago that basically allows you to kind of plot things quite easily. So if you click on gas oil ratio, you get the normal kind of gas oil ratio kind of plot. So above the bubble point is obviously a single number, and below bubble point, what's left in solution is obviously diminishing. And if you were to kind of zoom in here, so you can zoom in on the section, you can see that this red one is closest to the data point. If I choose another data point over here, again, the red one's pretty close. So kind of on average, it looks pretty decent, and the red one is indeed Glasgow. Oil formation volume factor is similar sorts of plots. Again, we're trying to use Glasgow. How good is it doing? Well, Glasgow is kind of missing a little bit there. Maybe, well, it looks like some of these others might be better. Vasquez-Beggs is not getting the formation volume factor too badly. What's GOR doing? Vasquez-Beggs is again this purple one. I don't know. You could choose either Vasquez-Beggs, you could choose Glasgow. Quite honestly, the result's not going to be that different. Oil viscosity, well, we don't really have a plot that we can look at because we've only got the one data point here, but at least the correlation is forced to go through that point. So for the purpose of this exercise, I'm just going to stick with The correlations I've already selected, and again, if I come out on the main screen, I see them here again. And you can choose them from here as well if you want to, but I'm just going to choose Glaser and Petrosky. And once you've actually run that matching button, match all, this thing here starts flashing at you to say you have run this calculation, but it doesn't mean to say that you've chosen the right options. But I'm pretty happy with Glaser and Petrosky. So has anybody got any questions on that bit? Hopefully fairly straightforward. So I don't hear anything that I need to react to, so I will carry on. Next up, I'm going to put in the Wellbore description. So I just come into this box over here, and I tend to use all and edit, which is kind of like a wizard kind of thing. It basically pulls up each of these boxes into these data entry boxes in turn. I'm not going to bother disabling surface equipment because I'm not going to enter any data for surface equipment, so we just ignore it. I click on edit, and then we can just go with each of these. So in here, you can put your deviation survey in, but it is a summary of a much larger deviation survey, and you have as many as 20 rows. This filtering option allows you to filter down a much bigger description into something that's not more than 20 rows. So I'm going to come in back into my Word document. I'm just going to cut and paste some numbers in here. Control V should work. And it calculates for you the whole angle, cumulative displacement, based on these measured and true vertical depth values. 0 represents a rotary table usually. No surface equipment, so I'm going to click cancel there. Don't need to enter anything. This is where it gets a little bit more interesting. We've got to put the Wellbore equipment in. So I choose tubing extending down from the wellhead. So the wellhead is actually 347.8 feet of water. So the wellhead is actually on the seabed. The tubing is going to extend down to 441.3 feet. Tubing inside diameter 3.96. I'm not going to worry too much about what the outside diameter is, although I can describe what it is here. And if you run calculations for what is happening at different points in the wellbore, so-called gradient calculation, these labels will appear in one of the columns to help you work out where you are in the wellbore. I'm not going to bother doing that here. Don't really have time. And it's 13 chrome tubing, so the roughness factor is this 0.0006 inches number. It's easy to work in inches for roughness values. So a good roughness value to use for, say, carbon steel or alloy steel is going to be 0.0018 inches. Really plastic coated tubing, which would be really smooth, that'd be 0.0002 inches. And for rough surface, could be like an open hole surface, or maybe a very perforated tubing, you can use 0.02 inches. That's about as rough as it's going to get. The rate multiplier here is just basically telling Prosper whether you have 2 identical bits of pipe or not, and each one is going to be taking half the flow each. If you wanted to do that, you just basically type in a half there. But we're not going to do that. It's just a single piece of tubing. Below that is a subsurface safety valve, which is just a point restriction here, which happens to be 3.75 inches. And then we have a little bit more tubing, quite a bit more tubing actually, 7 to 52.6 feet, 4.89 inches inside diameter, and again 13 chrome. Then the tubing changes diameter. So anytime you have a kind of change in diameter or change in roughness, you have to specify a change. This is why they call it nodal analysis, because these are the nodes of your system. So this slightly narrower tubing actually goes down to 7595.1 feet. Again, it's 13 chrome. Inside diameter is 3.96. And then right at the bottom of the well, we have a bit of flow in some casing. 8691 feet. Side diameter 6.09 inches, so a bit wider. So it's a little bit of flow in the casing, and then it goes into the tubing to the top of the well. And again, it's 13 chrome tubing, or 13 chrome casing in this case. So that's it. That's basically our wellbore description. We obviously need to use that to calculate vertical lift performance. Hit done here. Geothermal gradient. Well, I'm going to guess an overall heat transfer coefficient to begin with. And for an oil well, a good value that you might want to start off with is 8. Unless you happen to know that it's a little bit different. So in Rumaila, for instance, typically it's about 6. But for a lot of wells, it's about 8. And then we need to put in some details about what is happening. So at 0, Oh, actually, going to be modeling from the wellhead. Okay, so from the wellhead, which is at 347.8 feet, the temperature is actually going to be 40 Fahrenheit, which is kind of temperature at the bottom of the sea. This is your ambient temperature outside of your wellhead, and the reservoir temperature is 215.9 Fahrenheit. With that should be Control V, and this is the depth 8691. So this 8691 number is basically you can view that as, for instance, your top perforation depth, or maybe a mid perforation depth. Kind of depends on how you want to do it. I tend to use top perforation depth. So we don't need to do anything else there, and possibly just assume a linear temperature increase from there to there based on these numbers. The average heat capacities of the fluids, oil, gas, and water, I never touch these. These are quite good enough as they are. We do have a gauge, and we can say where the gauge is in the well. And the gauge is actually set at 4.2. Oops, I seem to be typing now in my Word document, so that's not very good. I need to come back in here. So 4.2, 72.6 feet. And you can just label that gauge. Done. The temperature at wellhead is not specified. I don't know what's happening here. Geothermal gradient, edit. Temperature at wellhead, 40 Fahrenheit. Interesting. Do I need to specify anything else? Temperature at wellhead. Turn on equipment, edit. Well, wait a minute, maybe I didn't put the numbers in properly. This is the usual thing when you kind of do things live. 347.8, geothermal gradient, 347.8, it's very fussy, right, okay, good. So that's that, and once you've done that, these kind of tick boxes have shown you what sections you've kind of filled in. And now we can move on to our IPR model. And then we can enter some well test data, match the model, and run some calculations. So IPR models. Okay, you've got a lot of choice on the left-hand side for different kinds of approaches. I see that there's already some kind of resolution problem. There you go, that's a little bit better. Let me try to maximize this so you can see the plot. There you go. And you can kind of move these things around as you want to. It's very flexible. So our IPR model, well, our reservoir pressure is 3290 PSIG. Reservoir temperature we already had, 215.9. The water cut, I looked that up from well test data. It happens to be 2.4%. There's our original solution GOR. Because the reservoir pressure is above bubble point, I'm not expecting anything other than original solution GOR to be produced. But if you've got free gas, if you're below bubble point, then obviously your total GOR can be bigger than your original solution GOR. And we think that the PI for this well, this productivity index, is greater than 200 stock tank barrels per day per PSI. That's a pretty high number. Most wells have a PI of 1, 2, 5, 20. this kind of a number, 200 is pretty exceptional. So we click calculate here and we get an IPR curve drawn up, and this red thing here is a temperature for different rates. So this is bottom hole flowing pressure and liquid rate. It's easy. That's basically that done. So if I head back to my slide pack very briefly, I describe some of these IPR models. So PI entry is the one we're using at the minute. The Q, the rate equals J, is the PI, this is a constant, times the drawdown, reservoir pressure minus bottom hole flowing pressure. This is top one. But you can choose Darcy, for instance, using the classical radial flow Darcy equation. You get the hydraulically fractured well models. In that one, you need to enter a dimensionless fracture conductivity. There's an equation for it there. There are horizontal well models. There's a no flow boundaries option where it kind of describes boundary effects caused by other wells. Could be physical boundaries as well, of course. But there are other options that allow you to calculate, for instance, constant pressure upper boundaries, which tend to be reservoirs that have reservoir pressure kind of topped up at the boundaries by things like, for instance, an aquifer or a gas cap. Multi-layer DP loss in Wellbore model we use very often. This allows you to calculate IPR curves for wellbores that have multiple completions in them, multiple layers. And the different layers can have different water cuts, different PVTs, different reservoir properties, and you'll get a kind of composite IPR curve at the end of it. What else? For gas wells, a little bit different. The classic kind of equivalent, if you like, of the PI model is the CNN model. Rate is a constant C times reservoir pressure squared minus PWF squared raised to the power N, hence CNN. And N varies between a half completely turbulent flow and one non-turbulent flow. The one we tend to use is the Petroleum Experts model, where you actually have to put quite a lot of reservoir data in there. Calculates it for you very nicely. And then there's Forchheimer, and Forchheimer with pseudo pressure as well. We don't tend to use those, but if you capture the shape of an IPR curve for a gas well in GAP, for an oil well, it will translate it automatically from whatever you've used into an equivalent PI model. For gas wells, the one you want to use is Forchheimer with pseudo pressure. That tends to capture the shape of the IPR curve better. So I come out of there, back into the software. So there's that. We now need to do some model matching and I'll run some calculations. So how are we doing for time? About 20 minutes. So when you pull up the VLP IPR matching window, is what it's called. This is basically where you put your well test data, and then you can then tune your model to the well test data. And the two things that we can be tuning here will be our vertical lift performance correlation. So we have to choose which is the best one to use, and then we're going to tune it such that it does actually calculate our measured downhole gauge pressure. And the other thing then we'll do that first, and then the other thing then we'll tune is our PI value, because at the minute we've just guessed 200, but that's not the real number. So these first two columns is just comments. Prosper doesn't use any of these, but for you it's useful. You can put the date in and what kind of test it was, whether it was a PLT or whether it was a well test or something like that. So before I put some numbers in, does anybody have any questions about this stuff so far? I know I'm rattling through this thing quite quickly, but with a limited amount of time, I have to be fairly pacey. Stunned silence. Okay, I'll take that as that I will carry on. Okay, so the wellhead flowing pressure in this particular test was 49.8 psig, quite high. Tubing head temperature 183.7, so quite hot at surface. Fluid is coming out at quite a rate, so the fluid doesn't actually have that much time to cool off, basically. Water cut 2.4%. Liquid rate, this is the interesting bit, 13,000. Oops, I'm typing the wrong place again. 13,798.6 apparently. although 13,800 is probably good enough. Now, gauge pressure. We have a gauge pressure of 2390.4 psig. Oh, sorry, wrong box. Control C. It's this one. I just need to put the depth in this box. Depth we had already. This is the 4272.6 feet number. Reservoir pressure we had already, 3290, not to be confused with gauge pressure 2390. Solution GOI is what we're producing, so 680.9 scuffs per stock tank barrel, and free GOI is 0. Basically, I tend to just put the total in this box here and put 0 in the other box. It tends to work reasonably well. So once you've done that, you just basically work your way left to right along these buttons. So estimate U value is the first thing we want to do. And it's actually calculating, instead of the 8 value we guessed earlier, actually for this one is actually more like 4.37. I can tell that the U value is going to be less than the value of 8 that I guessed earlier, because the wellhead arrival temperature is pretty high. It's not reservoir temperature anymore, but it's not cooled off much. So 4.37 is actually a fairly low number for an oil well. Unless you're working in, for instance, Alaska or somewhere like that, in which case the reservoir temperature is cold, everything is cold, it arrives cold, hasn't lost almost any heat because it didn't have much heat in the first place, in which case the U value could be very low indeed. So it's transferred this U value, it's actually transferred that value into our geothermal gradient model. It's replaced the 8 we had earlier with the good value. Now we can move on to correlation comparison. Now, before I do that, I'll flick back to my slide pack. And we will start talking a little bit more about these different flow correlations. So there are certain correlations that we use because they describe a boundary within which our gauge pressure should fit. So PEDEX took the Duns and Ross vertical lift correlation and adjusted it or modified it to basically overestimate the pressure drop in oil wells for the slug flow regime. So when the downhole gauge pressure is basically more than what this correlation would estimate, that you've probably got something wrong with your downhole equipment description or your well test data. But we'd never use this to calculate well performance with. This is just purely for a quality assurance purpose. Hagedorn-Brown is the classic one that was described in that SPE paper back in 1965. Fancher-Brown is another one that we don't ever use for well modeling purposes, but it's kind of the opposite of Duns and Ross modified. This doesn't include gas and liquid slip. So basically always underpredicts pressure drop. So if your gauge pressure is basically kind of to the left of what Fancher-Brown would predict, again, you've got problems. So you could have a problem with the fluid density or maybe the pressure reading on the well. The original Petroleum Experts model is a pretty decent model. It suits some wells, and you can see it's a lot of these things are kind of combination correlations. So you have this Gould and others flow regime map, which is used alongside Hagedorn-Brown for slug flow. It also used Duns and Ross original for mist flow and transition flow, and it uses Wallace and Griffiths for bubble flow calculations. So it's a combination of different correlations in one. If I go to this slide here, it was superseded by a thing called PE2, which is basically an enhanced version of the original. Which includes functionality for improved prediction of low rate vertical lift performance and well stability. So this is a correlation you can model most wells with. It's good for gas, it's good for oil, regular oil systems, good for water. So you can use it for water injectors, you can use it for regular oil wells. Really, really good correlation. The original Duns and Ross correlation is basically effective for mist flow, and it's got some enhancements there for modeling retrograde condensates. PE3 is basically the correlation we might reach for if you want to calculate heavy oils. PE4, PE5, PE5 extended, these are so-called mechanistic correlations which calculate things more from first principles. and tend not to be used for well modeling. They might be more suitable for flow line modeling, surface pipe work. But PE5 can be used for well modeling as well in order to help us assess a well stability. There's a function in there that helps us calculate if liquid films on the wellbore wall are actually flowing back down the well. In other words, it's indicating to you the onset of liquid loading. But we don't tend to use it for well performance calculations. For that, we'd either use P2 or P3. For gas wells, you have grey as an option. It has its own internal PVT model, but it was developed specifically for gases, and that's the one I tend to reach for gas. But to be honest, the results you get from grey is very similar to what you might get with P2. So that's kind of your choice. Anyway, that's the last of my slides. So I'm just going to go entirely back to the modeling. So if we go to correlation comparison, it's telling you what overall heat transfer coefficient we're using. It's the number we calculated earlier. And then we need to choose in here the various correlations we want to use. Now, I will choose Duns and Ross modified and Fancher-Brown to provide us with those extremes. And for quickness, I might just, well, we can choose Haggard or Brown, for instance. Some of these are more to do with kind of pipeline correlations, so I'm not going to select any of those. We'll select the original petroleum experts, PE2 and maybe PE3 just for a laugh, but we know that's not going to be particularly useful for us. Once you've selected those, it's populated in here for you, the data from the well test. So you literally just hit calculate, and there you go. Now, this is obviously only showing you results for the first of these correlations. It's obviously not much use to us, so I'm just going to go with, if I go to plot, I don't need the temperature curve, I just need the pressure curve. For the correlations I've chosen, hit done, and you get the real plot, what I'm expecting to see. And this is basically a calculation of pressure in the wellbore while the well is flowing at these conditions that we've specified. And there's a box here, you can hardly see it. Is that there? It's not a particularly obvious color, but it's a bit bigger than the others. That is our gauge pressure at the point in the well that we've got. So there is a little bit of an inflection point here, and it could be because the tubing is narrowed or something, or maybe there's a phase transition or something like that. But we need to see which correlation is closest. And if we have a look at Fancher-Brown, is this kind of dirty kind of color. It is on the very left as we're expecting, and our gauge pressure is to the right of that, so that's good news. This pink curve here, that's PE3, as is the heavy oil correlation. It's not particularly useful to us. Duns and Ross modified. Oh no, actually no, it is that one. Duns and Ross modified is this one over here. Sorry, the PE3 I think is this one. Actually, it shows you if you hover over it. P3 is that one. This one over here is Duns and Ross modified, and it should be the one furthest to the right. Our gauge pressure is between those, so that's good news. It seems like our model and the data is reasonable quality. If I kind of zoom in, what correlation is actually nearest to the gauge data, and if I hover over it, it's PE2, which is one we're expecting for this kind of fluid. So we finish here. We're doing for time, getting tight. Come out of here, I go into match VLP, in other words, tune the VLP, and I'm only going to choose the correlation I liked the most, and that was PE2. And I want to match it to our well test data, test number 1, and I literally click on where it says match. And it will come up with 2 tuning parameters. Now, unlike PVT correlations, both of these numbers are now multipliers. So the ideal value for each is 1. And because these 2 numbers are very, very close to 1, basically the untuned correlation is almost calculating our gauge pressure without having to tune it at all. We allow parameter 1 to be tuned to with no more than 5% and no more than 30% on parameter 2. Anything more than that, basically there's something wrong with the model or something wrong with our data. but it's well within that tolerance. So we'll accept those numbers, and we can hit done. So we've done the first three. Now we just need to tune the flow correlation. We now need to tune our PI value. All right, talking makes my throat dry. Okay, so we click on this one. We want number one, and we've chosen our flow correlation as well. And here you can see next to it, the name of the correlations are appended with those tuning parameters. Brilliant. And what PEDX does, actually, what Prosper does, it tries to minimize both of these values. I may as well choose a rate method geometric, which basically gives us a few more points at the low end of the range rather than the high end of the rate range. So we hit calculate, and I want the selected correlation, selected test. I'll hit go like this, and you can see we've got an IPR curve in red. This should replicate our IPR curve from earlier. This is our vertical lift performance curve here. I'm not going to describe right now why it's this shaped. That'll be the subject of a more kind of theoretical approach. I'm sure you've studied that many times. But if you zoom in, you can see that our test point is actually here, but the intersection point between the two curves is over here. And in order to try to make this purple box, for instance, fit exactly where this green cross is, in other words, matching our well test rate for the conditions we specified, I need to change the PI value. Now, for the interest of time, I'm just going to, you can click on IPR model, you go straight to your IPR model here, and I'm just going to adjust this value. And I know from having done this example in the past that the actual PI value is more like 285. It's this really big number. I don't need to click calculate here. I click done, but I do need to calculate back in this window. I do this routine again, and it's more or less converged. I look here at the percentage difference of the liquid rate is 0.37. It's a little bit too high. I like that value to be within 0.2%. So I need to adjust it. I need to adjust it down a little bit. The IPR is a little bit too high, so maybe it's more like 280 or something like that. There is an automatic means of doing this as well, but now this is within 0.2, so I'm a little bit happier with the quality of that match. So, and this well really did have a PI of this kind of value. It's pretty amazing well. So we've now tuned the model to well test data. We can now start running calculations, and the calculation option to use is this thing called system calculation. It doesn't upset the model that's underlying this thing, but it does allow us to run what-if calculations. So we can now start to see how healthy this well actually is. So I'm just going to replicate for now the well test data, and the well test well pressure was 1499.8. There's our water cut, there's our GOR. The default correlation is PE2, happens to be the one we want to use, and I will choose geometric again here. We want to calculate all for the entire well, so we just say bottom node there, and we hit calculate. And I'm calculating a liquid rate of 13,765, and the actual rate for the well was 13,799, more or less. So I'm a few barrels out in 13,000 or 14,000, which is fine. And this result table here tells you, what is the bottom or flowing pressure and all sorts of stuff. However, I may want to see, because the VLP curve here is rather flat, I'm a little bit concerned that if a reservoir pressure were to dip a little bit, or water cut were to climb a little bit, that it would affect well performance. And we can see how well performance changes over varying conditions by using this cases button. And I'm going to select several cases that we may be interested in. So let's do water cut first. So the current water cut is 2.4%, but what if it were, say, 5%, maybe 7.5%, 10%, say 12.5%, 15, say 17.5, 20, something like that. We'll just do water cut on its own. We'll keep everything else the same except change the water cut. If I now hit calculate, it'll rattle through these cases and then we can examine the results for each case in turn. So this is the results we've already seen for 2.4% water cut. This is what it is for 5. This is what it is for 7.5, 10. So have a keep looking at this liquid rate. Obviously, liquid rate is going to go down as water cut goes up. And you can see it goes down quite dramatically. And then all of a sudden, between 15 and 17.5%, the well's dead because VLP and IPR curves are no longer meeting. And this table is obviously empty of data. Even at 15%, you know, these two curves are barely touching. I would have thought this will be either dead or unstable. It's a little bit better at, say, 12.5% water cut. It's a little bit healthier at, say, 10. So I would say if the water cut creeps up to about 10, we'll probably still be okay, but the well is going to be basically dead soon afterwards. So it doesn't sound like a particularly healthy well to me, even though we're producing 13,000 or whatever it is barrels a day. This is not, you know, necessarily particularly intuitive kind of stuff, and you need to do the modeling in order to show this. Now, if you wanted to show the effect in a plot of the different cases, you can just use sensitivity plot. And if I go to variables, I can plot something a bit more interesting. Let's say, you know, liquid rate or something like that. Here it is. So that's a plot of water cut versus liquid rate. You can see that the rate is nose diving as the water cut goes up. If, for instance, in one of these particular cases, let's say at 10%, I want to calculate the performance within the wellbore itself, you can do pressure, sensitivity pressure versus depth. And you simply select it and hit calculate, and you get this massive table of results here of what is happening in the well at different depths. And if I'd bothered putting those labels into my wellbore description earlier, you would have seen those labels in here as well. You can see where the gauge is and all of this kind of stuff. So it's pretty useful. If we weren't interested in, for instance, water cut, we can change the case, so we can just reset everything. And instead of water cut, we could look at reservoir pressure, for instance. How are we doing for time? We're overrunning a little bit. Let's have, say, 3290 as our base, but if it went lower than that, for instance, 3250, 3200, 3175, say 3150, 3125, and say 3100. I'm not sure when it's going to conk out, but we'll set those up as cases instead, run those calculations. And again, we can just rattle through them. So we start with 3290, our current case, but if the reservoir pressure were to drop, you can see the rate dropping like a stone as well. And somewhere between 3175 and 3150, the well dies. So we haven't got to lose that much reservoir pressure for the well to be in serious trouble. And for instance, if you were to do something like, I'll make this one the last one if I just reset everything. Let's say we look at what is known as top node pressure, in other words, wellhead flowing pressure. We had 1409.8 as the base case, but if the wellhead pressure were to go up a little bit, for instance, back pressure caused by other wells flowing into the same manifold or something like that, what happens then? So if we went to say 1425, 1450, 1475, say 1500, 1525, and say 15. Oops. And say 1550. Done. Here are our new cases. Calculate them. And so this is what happens at 1409, but rate obviously comes down as wellhead pressure goes up. And you can see that actually, if the wellhead pressure were to reach about 1500, roughly 1500, a well's going to be in a lot of trouble. So yeah, and again, you can do pressure versus, not pressure versus depth. I'm going to do sensitivity plot. And you have to change the variable. So instead of liquid rate this time, okay, that's fine. So liquid rate versus top node pressure, and you can again visualize how the rate drops off. That is literally about all I've got time for. I guess I need to hand it over back to the room and see if there are any questions at this stage. And I'm hoping that this was kind of useful for people. I know it's a bit quick, but
yeah. So I'd like the audience to Peter. There are some questions in the chat. I did see one earlier, so maybe if you want to answer that question, and if anyone wants to answer any questions just now, please put them in the chat or speak up to the mic, please. Thank you.
Yeah, pleasure to take them. So what are the chat questions?
If you open a chat, Peter, you can see them at you'll see a list.
All right, okay.
Hello.
Okay, PVT matching, how often is this process done? Okay, so not very often. Once you've established what your PVT model is, you basically don't touch it. The only reason you might want to change it is if the separation pathway in the field, it becomes dramatically different to what it was when you exported the black oil model from the equation of state in the first place. In which case, you're going to go all the way back to your equation of state model, re-export your black oil model with different separation train conditions in mind, and then calculate a new set of black oil model data that you can then put into Prosper. But you don't need to do this very often. I've rarely seen it done, in fact. So hopefully that answers that question for you, Jesse.
Hello.
Hello.
Am I audible?
You are, yeah, absolutely.
Hi, Mr. Mihalik. Well delivered presentation first. And I have a question. Yeah, I have a question. Like, how do you model a well which has been recently fractured? Because ultimately the reservoir parameters changed after you frack it. So how do you estimate the reservoir parameter like porosity and permeability in that condition?
Typically, you might be using another software package that would model the fracture for you. But in Prosper itself, if I just go back to the software for a moment, in the IPL model, instead of using PI entry, you've actually got these different options in here. So there's one for hydraulically fractured well, and there's also another one, horizontal well with transverse vertical fractures. They're the ones where the fractures are kind of at 90 degrees to the wellbore. These models are fine for reservoirs that have a reasonable permeability, like let's say above 10 millidarcy. Or above, once you start going below, like 0.2 millidarcies or something like that, you start getting into kind of tight rock. Then really, you need to calculate an IPR not with Prosper, but you need to go into it's another it's another suite in the software package, and you can just go down to Petroleum Experts. There's a whole list of these things in here. This one called Reveal down here is a numerical reservoir simulator for near wellbore studies. And you'd use that one primarily to calculate IPR models for kind of for tight wells if you've got multiple fractures. But MBAL itself has also modeling routines for tight oil and tight gas reservoirs. So you typically get the IPR model maybe from that and then tie that to a wellbore description via GAP. So a number of different ways of doing it, but for kind of for formations that are reasonably high perm, then you can choose, for instance, hydraulically fractured well. But then you've got to put in a bunch of data in here that supports that dimensionless fracture conductivity value that I mentioned earlier. Fracture half lengths, which is kind of half of the size of the fracture you might have, and there may be some means of estimating, how wide the fracture is and how far it extends from the wellbore. Deep shape factor, I didn't go into kind of Darcy modeling, but deep shape factor is a type of skin value that kind of describes where the reservoir is in the reservoir. So if the well is in the kind of the middle of a circular drainage area, that would be the highest deep shape factor that you can have, of 31.6, but the number diminishes if, for instance, the well is in the middle of, for instance, in the on one end of, say, a long rectangle or something like that. But you got to put in these numbers in here. And this transverse fractures thing, again, you've got even more stuff to put in. And you can put kind of skin values and this kind of stuff. But I didn't talk about Darcy modeling today, but I just tried to keep it simple with a PI entry. Does that try to answer your question?
Got your point. Okay, thank you so much.
Yeah.
Can I ask one more question, if
Sure.
you allow me? Okay. How do we do the bean size optimization using Prosper?
Did you say bean up?
Yes, bean size optimization, bean size modeling, choke modeling, choke performance.
Yeah, so let's say, for instance, that let's say you've drilled a new well and you've got and you want to bean up the well. Typically, you might be defining a bean up schedule. And let's say for the first 15 minutes or whatever, the choke, you want a certain amount of drawdown applied. And then over the next 15-minute period, it's a slightly different drawdown. And then after that, and another 15-minute period, there's another a choke setting change that allows you to apply a slightly higher drawdown. What you can do, and I have done it in the past for beaning up new wells, you can actually hook up your well model with the reservoir model in GAP. You can run a performance prediction whereby you actually use Open Server, which is actually a kind of a programming language that sits underneath Prosper or MBAL and GAP. In this particular instance, it would be GAP. And you can basically do some coding in your spreadsheet to take advantage of this in order to get GAP to run calculations for you in a sequence of calculations every 15 minutes, whereby you calculate what choke setting you'd need to achieve a certain drawdown, and from the choke manufacturer you can get hold of this choke performance data that tells you what the size is for a certain stem position. And what you're trying to do is calculate a choke size, which then allows you to achieve a certain wellhead flowing pressure, which in turn allows you to achieve a certain drawdown. But you do have a choke performance calculator in Prosper as well, for pipelines and things like that. And you can get it to calculate what you want to calculate, and you give it certain start data. So for instance, if I want to calculate a pressure drop, we usually use the ELF flow, ELF choke model, which is a good one. You enter gas oil ratio, the water cut, the inlet pressure of your choke, the inlet temperature, the liquid rate that you're interested in, and a choke size as diameter, and it will calculate for you the outlet pressure, the outlet temperature, the critical pressure, critical rate, and critical temperature. And if you wanted to, when you hit calculate, it says, do you want to create the plot as well? And it will create the plot for you. And what you'll end up with is, if I just quickly draw this thing out for you, you'll get a plot that looks a little bit kind of like this. And hopefully you'll be operating your choke. This is pressure, if you like, kind of downstream of the choke, and this is Q up here. But what happens if you keep reducing pressure downstream of your choke, the operating point moves upwards according to this curve, but it will eventually flatten out. And then no matter how much you reduce the pressure downstream of the choke, you're not going to get any more fluid rate going through there, because physically you can't fit any more molecules through that space.
Okay.
So this is a long-winded subject, and it's kind of programming in Excel and hooking Excel up with Prosper and this kind of thing. It's a little bit long-winded. It is doable, but it's not super straightforward. But you could just calculate it manually. If you know what the reservoir pressure is, and pressure is not going to change that much while you're beating the well up, that remains constant. A water cut will be constant. PI is probably going to be constant, whatever you decided it might be. And then basically you can calculate just manually what is the let's say you can determine what the wellhead pressure would be to achieve a certain drawdown, and say, okay, so that's the wellhead pressure I need. But you could then calculate the well with a wellhead flow line attached to the wellhead, and you can put a choke in there as well, and you can then calculate what choke diameter you'd need to achieve to get that certain wellhead pressure. And then you keep going to calculate different drawdowns depending on your schedule, and you can work back from that what the diameter is, and then from your choke performance data you can calculate for a certain size needs a certain stem position. I have done it before. It's a bit long-winded, but it's doable.
Okay, good.
Yeah, bit of a rambling answer, but I think you got the idea.
Actually, I was interested into this. Actually, we generally do it on our site by using generally three size of beams testing, and then after we choose the optimal beam size. And I was curious to know if Prosper can provide the optimal beam size.
Yeah, you can get it to do that, because you can attach a flow line to your wellhead in Prosper, and you can insert a choke in the system as well. And then you can basically fiddle with your choke to achieve certain flow rates, which obviously reflect different drawdowns.
Okay, thank you so much.
It's all right. Any other questions? I don't know if participants would fancy another session at some other time, maybe covering a slightly different subject, maybe water injectors or whatever.
Yeah, I think that's it, Pete. There's no further questions, then we'll end it there. I think it's a great session.
Okay, that's fine. We overran a little bit, but hopefully people thought it was interesting.
Yeah,
I appreciate the opportunity.
Yeah, so thank you to everyone who turned up. Please look out for future SPE YP events. We've got a couple exciting ones coming up. And thank you, Peter, for doing this for us today. It's very helpful.
No problem. I hope people enjoyed it.
And also, I'd like to say, if any of you guys have any suggestions for any future events that you would like Peter to, any topics that you would like to bring forward and present, then Peter's happy to do so. So you can send us an email or any suggestions, and we'll look at them.
Yeah, I'd look forward to it.
All right, thanks, guys. I'll end the event there. Yeah, thanks, Peter. Have a nice evening now. You can relax.
Yep, you too. Take care, everybody. Thanks for dialing in.
Yeah.
Excuse me.
Hello.
Hello, Peter. Thank you for this informative exercise. I would like to ask, forgive my ignorance, I would like to ask if there is a margin of tolerance for the software.
What? Sorry. So, what was the question?
A margin of tolerance for the software. An error margin.
Well, as you can see, when we matched our well model to well test data and we replicated well test conditions, we almost got the same rate. It was only off by maybe 30 barrels a day or whatever out of nearly 14,000. So you can, it kind of depends on what it is that you're trying to calculate, but Prosper can deliver pretty decent numbers.
Okay, thank you.
I don't know if that answers your question particularly, but it kind of depends on how well you've described your wellbore, how accurately you might have tuned your well model to well test data. Have you chosen the right PVT correlation, for instance? Have you chosen the right flow correlation? All of these things can help if you optimize those. And then hopefully you get decent results at the end of it. but there's no reason to suggest that Prosper can't handle decent numbers for you.
Okay, so it depends on the input.
Yeah, absolutely. I mean, it's the usual thing with software: garbage in, garbage out. It's the same with any piece of software, right?
Indeed, yeah.
Yeah.
Thank
But
you.
if you're prepared to put in a reasonable effort to try to get the model set up decently, then it can provide you with some very decent numbers.
Very good. Thank you very much.
No problem.
Okay, Peter, I think we'll wrap it up there. I think your host, so if you end the session, it will stop the recording as well for us. So.
Perfect. I think I can actually hit the stop record button myself. Actually, I can see that my mouse becomes active, so I will do that. Thank you, everyone.
Thank you.
Thanks.